Humans' mind and language doesn't cease to amaze me, and that's why I do research on it and indulge in reading recent research papers in this field. HippoRAG is a paper that came out last month and is allegedly inspired by humans' brain and hippocampal memory, the neocortex and hippocampus, and how they index humans' memory and experience. And they also blend this idea with other algorithms that we had in computer science for over 2 decades to build a better RAG systems, or retrieval augmented generation systems. So please join me in enjoying our step-by-step walkthrough of this paper. Alright, let's get into the paper, HippoRAG. We have 2 goals here. The first goal is I'm going to explain the paper step by step and simply, but not oversimplified by using excessive analogies, so that we don't get into this point, which is an overestimation of our knowledge and false confidence. We have an interesting phenomenon, I'm sure that you have experienced that, valley of false confidence. When we know a little bit about something and we have a general idea, we tend to overestimate our knowledge, and when we go and read more about that, we get into the valley of despair. We feel like we know nothing, and then we get out of that to hopefully reach a point that we have a practical standpoint over limitations and also the use cases of the approach. So I'm trying to get everyone, including myself, from the very beginning up to this practical standpoint, this slope of enlightenment. And the second goal is, I see some of my friends complaining about not having GPU or similar sort of issues. If this is the only problem that is preventing you from running and working with the state-of-the-art models, I'm going to help everyone to navigate this problem, to work around that by using Google Cloud GPUs, especially Google Colab. Okay, let's get into the paper and explain that in part 1, and in part 2 we will explain the code. We have a framework for reviewing research papers, which is problem addressed. We will discuss the problem that they're trying to solve and their motivation, why the previous approaches were insufficient, and then we will explore their approach and their evaluation and the result, and also we will reflect on our learning and research ideas. Problem addressed. Okay, so imagine that we have a language model, chat AI, and we want to train that. We collect the data from the internet, probably up to a specific point like January 2024, and then we train the model. So the model is unable, obviously, to answer the questions about February 2024 because we didn't train the model over that data. So the model is not able to answer the question about the point that their data point was not in the training set. So how can you address this problem? Or a similar situation, imagine that you have a pile of documents, pile of private documents, and you want to ask question about your private documents. Language model is not trained on your documents. How can you enable a language model to answer a question which is answerable by reading your private documents? The framework that we have for addressing this problem, which is called New Experience Integration, is RAG, Retrieval Augmented Generation. And also we use knowledge graph technology for improving RAGs. So RAG is very simple. You have your documents and you index them, you figure out what are the topics, and then so that later that you get a question, you can go and retrieve the most relevant documents related to your question, so that you can select the top 5, let's say, and then feed them to the model so that the model can answer your question based on the new experiences in February 2024, what happened in the February 2024, or the new or the private documents that the model hadn't seen during the training. So this is a problem that we have had, and they have written that they are trying to make a improvement over knowledge integration, but I read their paper from A to Z, and this is not the problem that they are directly solving. They are directly solving a problem that we had in retrieval part. So we will discuss that in the third part, proposed solution, but right now this is what they have that they are trying to address. Why the previous approaches were insufficient. Previous current RAG systems that they rely on encoding the document or the chunks, they only encode the documents in isolation, and they don't look at the connections and association between those documents. So let's consider this example. Imagine that we have a lot of documents about Stanford and Alzheimer's disease, Alzheimer research group. So we have, for instance, one document about Dr. Thomas, which is working in Stanford, and like 2 or 3 pages of in one passage, and then we have a passage about Dr. Eva, or we have a passage for Dr. Jack working in Stanford. Imagine countless or many documents that we have for Stanford professors, and then we have a lot of other documents about professors that they are working on Alzheimer and disease and their approach for solving that. So imagine that we receive a question as a human, and we have all of this information in our mind about who is the Stanford prof who is working on Alzheimer as well. So as a human, in our mind we have indexed the professors and also Alzheimer, and in between them we have intertwined mapping that maps or stores the associations and helps us in retrieving the answer of this question about the professor who is also working in Stanford and who is working on Alzheimer. So when we get this question, Stanford and Alzheimer, we can find the person who is associated to these 2 topics. But current RAG systems, they encode the documents separately. So the topic in the questions are Stanford professor, Alzheimer disease. So we have countless documents that they are talking about the Stanford professors, and other documents that they are explaining the research papers in Alzheimer and the professors that they have worked on this. So if we get a question, we don't know how to retrieve the relevant documents because they are not considering the associations between them. So HippoRAG is getting inspired from a human's mind to build a better knowledge graph, which will eventually help us in retrieval of the most relevant documents so that we can answer the questions appropriately. All right, let's discuss the proposed solution. The upper part is about the when we ask a question, but everything that we have below here is for the indexing time. When you have lots of passages and you are trying to find or generate a mind map or knowledge graph over that, and we call that indexing. And then the upper part is the query time or inference time or retrieval or online retrieval part. So there isn't any picture for the pipeline in the research in the paper, and the only thing that we have here is a nice diagram that they have for explaining some concepts, but there is no graph visual representation of their pipeline so that we can understand everything clearly. But good news is I have brought that here, so please bear with me for the next 3 minutes to real quick discuss that. Okay, first we have a collection of private data or private passages or everything that has not been in the language model's training corpus. So we first pass all of the passages to an embedding model so that we can store their vector representation there. And about the embedding model, embedding is a model that takes one paragraph or word or a passage, any natural language input, and then it will categorize it, will put them in different spaces. Imagine that you receive a bunch of books about chemistry, physics, and you are and you try to make sense of them and put them in different places so that you can retrieve them faster when somebody asks you about give me a book that talks about like relativity theorem. So you will go to the bookshelf that is for physics, and then you will go through the bookshelf to find the relevant book. Embedding model is similar. You pass documents or words and it will put them in different places in the space so that all of those documents or words that they have got together, they have been placed together or close together, they have some sort of similar idea. So this is about embedding model. But we don't have a bookshelf in computers. We have a space. We try to represent them with numbers, and that's why we have some numbers as an output, which means that, okay, so the document that we received, the first document is about math, we put that in position 0. This another one, we put that in position 5 about chemistry. So yeah, this is how embedding works in general. And we have the corpus, and then we try to extract named entities, the special names in your documents. So imagine this input paragraph, human paragraph. Hello, it's Reza working at U of L, and the name entities that are extracted are Reza and U of L, because those are two names that they are pointing to a specific object in the word. And the code that they have here is they have prepared a sample for language model to give them an example so that they can extract the name entities correctly in a correct format. They will give a passage with the example, and then they will ask language model, okay, go and extract the name entities. Once you have the name entities extracted, you go and extract triples. So let's go to the language model. We first ask the language model, okay, here is an example how to extract name entities, and then this is a passage, extract name entities. It will extract them, Keynote, Dr. Marcus, and Laura, Alberta Innovates, and other named entities. And then we get this name entity and pass to the model and ask another question. Okay, now that you have named entities, go and extract triples. Triples are a subject, object, and the relation between them. Keynote title as is a relation, opening ceremony, or Dr. Marcus Collins is a relation, is a relation, Marcus is a named entity, and award-winning marketer and cultural translator. So cultural translated was not in our named entities before, because it's not pointed to a specific object in the word. It's a noun phrase. So let's go to the code that they have. In the second part, they ask language model specifically for two things. They ask, pay attention. Okay, your task is to extract triples, but pay attention to two things. First of all, clearly resolve pronouns to their specific names, so that if you get he should be translated to the exact person that is referring to. We don't want to have he or pronouns in our knowledge graph. And the second of all, in each triple should contain at least one, but preferably two named entities in the list of each passage. So it will ask the model to extract triples, but with having much more emphasis on the named entities. But you are also allowed to extract noun phrases if you see that there is a relation between named entity and a noun phrase. So this is how they extract the triples. And once they have the triples, they think three things. First, they again pass all of the nodes, all of the noun phrases and name entities, or we call them nodes of the graph, to embedding, so that we can get the embeddings. And also they generate the knowledge graph. For instance, if Dr. Thomas is working on Alzheimer, we have Dr. Thomas connected to Alzheimer node. And if Dr. Thomas is working in Stanford, we have the same nodes and connection between them in the graph. And we also have another thing. If there are two nodes, for instance, if we have one node called Stanford and another node called Stanford University of America, then these two also get connected, because they're based on their embedding, we see that they are too close to each other, and they should probably be connected to each other. So we add similarity edges into the knowledge graph as well. And then we construct another thing, node and passage occurrence metrics, which simply says Stanford, what are the passages that Stanford is showing up in them, so that we can use that later to retrieve the passages that are related to Stanford. when we get a question about the Stanford. So this is the indexing time when we, for instance, in our exam night and we are trying to create a mind map. Let's go to the exam day that you get a question. So who is the Stanford University prof that does Alzheimer research? First, we extract the name entities from query using our language model. This parrot is representing a language model. It's a funny symbol for language models. And so Stanford University and Alzheimer were detected as name entities, which is correct. And then we use language model and embedding model and embeddings of nodes, this thing that we generated before, to map these name entities to the nodes that we have in our knowledge graph. So we find the similar nodes, which are Stanford and Alzheimer, and then we go and find the probabilities of the most important nodes. The initial probability is assigned 1 and 1 to all of the name entities that we had in the query. But we can also improve that by seeing which of these name entities in the query were more important. Imagine you have a pile of documents about skateboard, different techniques, and you have also one specific document about injuries, for knee injuries of a skateboard. If somebody asks you a question, what are the I'm using a skateboard, what are the knee injuries? So a skateboard and knee injury should not have the same weight, because a skateboard is literally appearing in all of your documents, because all of your documents are talking about a skateboard, but one specific document is only talking about knee injuries. So we use this idea of the number of times that one name entity appeared in the number of passages that include that name entity, so that we can adjust the weight. Those name entities that appear in less documents, they have more weight. They will get more weights. That's why Stanford is adjusted to a higher weight than Alzheimer. And then this is the interesting part. This is what we were describing in the paper. So when you get Stanford and you get a question about Stanford prof that is working on Alzheimer, you don't just go and retrieve these two nodes. You also go and see the relevant nodes that they are associating with these two nodes. So in this part, we run personalized PageRank to get the most relevant nodes, other nodes about these two topics by using our knowledge graph, so that we can get the final probabilities of nodes. And that's why you see here Dr. Thomas has got some weights, and other nodes that we had here, they also have got some very little weights. And so based on these probabilities we rank the documents. But what if the question that you got had some name entities that you didn't have a similar name entity in your knowledge graph? That's where we will use these passages, embeddings, to retrieve the most relevant documents, so that we have a backup plan if this fancy pipeline that we have designed didn't work well, didn't extract the name entities and we didn't have any similar name entities in our knowledge graph. In that case, that we didn't have any similar name entity in the query to the knowledge graph that we had, we will go and find we will embed this query and find the relevant passages, and then pass that to the final language model. Okay, so that's why we need the passages embeddings if necessary in this part as well. So finally, we select the top K documents, and then we pass that to our parrot, to our language model with initial query, and then we will get the final answer. I have collected a couple of touchstones that I use for evaluating my own work and other people's work. which are listed here. Are they cherry picking? One thing that we have to keep in our mind, that the examples that we see for different tools or research papers are usually cherry picked, which means they have selected the best example that their model could possibly generate. So we have to keep in our mind that we should not get biased by their example, and we have to go through the whole details. Is their approach statistically significant? The fact that we have in training language model is that randomness is involved, and we have to err on the side of caution by doing some statistical significant testing to see if the improvement is coming from a genuine algorithmic improvement and not just randomness. So they have mentioned that they have done their model result in significant improvement. I asked them, you mentioned result in significant improvements. How did you calculate that? Could you please elaborate on details? Thank you. And they have mentioned that we did not do any specific significant testing. We will change the wording in the future versions. So they have not done any significant testing, and this is not unusual. Many research papers do not do that. I don't know why, but their improvement is considerable, especially on Wikipedia dataset. They have increased that quite considerable. So we cannot use significant, but we can say that, okay, the improvement is considerable. And another factor is their approach practically significant? In practice, in real world, in deployment, we have a whole different scenario. We have a whole different story. You have to take care if the model is easy to set up. This is very important. If the model is using RAM appropriately, if the model is using GPU moderately, there are many factors. If the code base is easy to maintain, an improvement for future, and there are many factors. So they have mentioned here in the last part of the conclusion and limitation that we are yet to empirically prove the efficiency of our index, of our knowledge graph, as its size grows rapidly. So the graph that we discussed that they have in their approach, this graph, its size grows rapidly. So this is one practical limitation that we have to keep in our mind, and if we are trying to implement that, we have to address that. So are they sweeping the limitations under the rug? They have done a great job in revealing the limitations of their work in part F error analysis. They have gone through different parts that their model, their approach is falling short. For instance, they have mentioned that the language model that they are using is not always accurate in name entity extraction, or they are not selecting all the OpenIE or triples. So they have done a great job in exploring the limitations. And about the missing OpenIE, I think that we can ask the language models a couple of times to reflect on its answer so that we can get all the possible triples. So here the language model generated the name entities and triples, and I asked that they don't use that in their code. So I asked the model to reflect on your job and see if there is anything missing. You missed some triples. Do that again with great attention to the details. So the model, these are the first triples, and the model went and extracted more triples. Like Dr. Marcus will unpack how to leverage culture to drive action, but previously we didn't have that. Dr. Marcus will unpack, will unpack. I also asked again, I think in addition to the triples that you have extracted, there are more triples. Is there, if there is no other triple, because I'm just bluffing, I'm not sure that if there is anything missing or not. I'm just using iterative method for over language model so that I can get a better answer. So if there is no other triple, just simply return your previous output. And it got and extracted even more triple. So I think it is quite enough, and then I stopped that. So we can use iterative approach for tackling this problem that they have mentioned here, incorrect or missing open, i.e. or triples. So are there any confounding factors? Confounding factors are extremely important and extremely hard to find, and only honest researchers will reveal their confounding factors and try to address that. Are there baselines? The most recent year they are not using any baseline from 2010. Or where is the creativity or novelty? It's very hard, especially nowadays, to come up with a totally novel or creative approach, but their creativity is coming from juxtaposing different algorithms that we had before that no one could perceive that we can put them together and improve the result of RAGs. So this is their creativity. Reading this paper had a couple of interesting realizations for me. I will only mention one of them. So I will reading this paper and I realized that, okay, in my previous lecture that I had, the session that we had on design patterns of machine learning, I mentioned that we have tasks that we try to tackle that, like summarization, and then we have metric, loss function, and model that should be chained so that we can tackle the task appropriately and efficiently. But I didn't emphasize on the benchmark. I realized that I have to emphasize on the benchmark, as it can sometimes introduce a gap between our effort in the model part and the final end of the chain, which is the task that we are trying to solve. Okay, so one thing, first of all, sometimes the task is not quite well defined. For instance, AGI, artificial general intelligence, nobody can define this task, and we don't have appropriate benchmark for that. We have some like benchmarks for IQ or other benchmarks, but they are not totally reflect the final task, and this benchmark is also introduced another layer, another gap between our effort in the model part and the final objective, which is the task that we are trying to solve. And also I realized another thing, which is similarly in the research field that I had, text summarization using language models. I realized that the benchmarks like CNN Daily Mail, Exxon, they are stagnant. They have been around for quite a while, but the models, the improvement that we had over the last years, they need new benchmarks, but we are using the benchmarks that had been around for quite a while, and we have a stagnation here in this part, which is not quite desirable. And we have that again in the question generation as well, and it is the whole idea of the realization that I had is it points back to the paper, that how humans brain work. I read this paper, but it had an indirect implication in my mind. I realized two different patterns in two different topics, and I could find the pattern and see, yeah, okay, they are overlapping, and we have stagnation in summarization benchmark, and we have that in question generation as well, and it is probably the case in whole machine learning area. So it was interesting for me. Couple of new directions came to my mind for improving the result. I have mentioned first one of them, which is iterative approach for name entity recognition that we discussed before. The second is we are not considering relations in our knowledge graph. So I was asking them why you didn't consider that, and have you seen any research paper that is using a schema-less knowledge graph and is also considering the relations? And they told me that no, I haven't seen any research paper tackling this problem yet, but they are probably coming out soon. So this is another direction. And the third one is I always get inspiration by humans' mind and how humans are solving a problem. So imagine that we have this simple scenario that you have one final exam for a textbook. You just simply go and memorize everything. This is similar to the approach that has been used in this research paper. They go to the passages and construct the knowledge graph, the triples, and then with the method that we discussed in the previous parts, they find the relevant passages. But what if you have something more complicated with more documents? And that speaks to the problem that they mentioned here. This is a very important problem, the scalability. They mentioned that its size grows rapidly. So how can you find relevant passages when first of all the size is growing and also the time for searching scales similarly? So one approach is when you have a complicated scenario with having many documents, we can think of that as a entrance exam. For instance, in my country, we have entrance exam that you have to read different subjects, math, chemistry, for the whole high school for the last 4 years, and you have to answer the questions in a couple of hours related to these topics. So what my mind was doing was so this is the first part. Indexing is the time before the exam. So I was trying to construct, first of all, understand these topics, understand what they exactly mean, which means connecting them in a meaningful way, constructing this graph, and also I was constructing one indexing layer, schema upon that. But my schema was hierarchical. So I had math, and then on the another layer I had first year, second year, third year, fourth year, and then it had in the final layer of schema different subjects, for instance like integral or geometry, or different subjects that we had. And different years of physics can also point to the subjects that we have in math. So it helped me significantly in finding the relevant nodes of the knowledge graph in the very short spell and duration of the entrance exam. For instance, I was reading the question, and the question was about math, and I was trying to find, okay, in what year is exactly this question, and then I was finding the specific topics, and then I was fetching in my mind the relevant information for answering the question. So what we can do is, and also the nodes were linked to the passages. Right now in the approach of this paper, nodes of the graph are not directly linked to the paper. When we get the final probabilities, the most likely nodes, we multiply that into this graph. But we don't need to do this extra operation. We can also add a passage ID to all of these in the nodes, so that we can fetch the relevant documents faster. So what we can do practically is, first we do the triple extraction like in the similar manner that we discussed so far, and then we fed them to the language model, or most important one of them, so that the language models can detect the subjects. And then we construct a hierarchical schema, exactly in the same manner that Raptor architecture was coming up with clustering documents and summarizing them. But we cluster them and create a schema label, so that we can have a hierarchical schema on top of our knowledge graph. It's like a B-tree. All right, this was about the other directions. We discussed 3 different new directions. Now let's get to their code and run that on Google Colab. All right, let's see how we can run their code. First of all, you have to have the GPU enabled. You can change the runtime here. Go to change runtime type and select GPU. Change the CPU to GPU so that you can get a free GPU on Google Colab. And then we need to install Conda. And a Conda is a tool that we use for setting up the environment, so that we can replicate the result and have the isolated environment from the rest of the operating system. So let me run this cell, and I have got this idea of how to run Conda on a Conda in a better way from these 2 resources that you can check later after this video, because I'm going to share the code and also the dataset that I'm using with you. So the dataset that I'm going to use, and sometimes the Google Colab crashes, you can restart the Google Colab. It sometimes happens. So let me upload the dataset that we have. The dataset is our inventors dataset that we discussed in previous videos on RAG systems using Raptor. It should be formatted in the following way. It should have title, text, which is the text of the session, and also the index. And we have 186 sessions. So this is about the dataset, and we have discussed that in previous videos. Then we go through creating our environments and pulling the code, the HippoRAG code from the repository. So this is the repository. We download all of their code on Google Colab directly. You don't need to do anything on your personal computer, on your own system. Everything is on Google Colab. We clone that, or we download that, or pull that, and we change a couple of things here. I have updated the Hugging Face because there were some issues with the previous versions, and it is also mentioned in their GitHub issues. So if you go here, they have mentioned that there are some issues with the new version, with the previous version of Hugging Face, and they have suggested that we should have to change the Hugging Face version to the newer version. Okay, after installing the environment, the requirements, we get some errors. You don't need to worry about this, and then we download our embedding model, which is Coolbert version 2. And the good news is you don't need to download this large model on your system, and we do that quickly on Google Colab. And then we you need to have Open AI API key or Together AI API key stored here, and then you can use them for generating the final answer. We need a language model for the final part of the chain for passing the query, and the retrieve documents for generating the final answer. So this is about the API keys, and then we change the address of NLTK, the packages of NLTK. Then we will get to the bash file that runs the offline indexing part, and I have unpacked the code here so that you can see what is inside that bash file. We set the environment variables, the dataset. Our dataset names is Inventors 2024, and the retrieval, which is Coolbert, language model, and everything else. Number of passages, I'm going to only construct the knowledge graph and pre-process the first 4 passages, because it will take a lot of time to construct knowledge graph or extract name entities for all of those 186 documents. So I only use the first 4 documents, and the rest of that is just following the steps that they have mentioned in their GitHub repository. Here, all of the steps that they have mentioned here, and then after running this part, we have the index, we have the what we discussed previously. After running that, we will have the node embeddings, the knowledge graph, and node passage metrics, which will be used in the next part, which is the online retrieval, that you can ask a question from the user. So we have a problem here, and the problem is the dataset should be in the data directory. We didn't put that in the dataset directory. So let's grab the inventors and put that here under data directory. Okay, so we should be fine right now. Let's run that again. Okay, it is extracting OpenIE or the triples. It saved the triples in OpenIE Inventors 2024. Let's see under outputs. Let's see if they are here. OpenIE Inventors here. So we have the triples here. So document the title, text, and then we should have triples somewhere here. Extracted entities. So exhibition hall, inventors, MacLoad, Foyer, networking, all of the entities, and extracted triples. Session 3 is a session under networking. Session 3 title as networking breaks, and all the triples are stored for the first 4 documents. So after running, then we have our retrieval model, the model that we can use for asking a question, the model that we can pass the query, and it will automatically handle the rest of the pipeline. And where did I find this model? I changed the code that you see here to write the pipeline for the online retrieval. So let's close this part and then wait for the pre-processing of the data, so that later we can ask a question like what is MacLoad Foyer? I'm not sure about the name of this place, but anyways, so let's wait for the model to finish the indexing. right, the model finished the indexing, and then we are right now able to ask a question from the model. For the first time, it will take a little bit time so that the model can cache all of the components that we have in the pipeline. But for the other questions, we don't have any delay in answering the question. It is only for the first question that you ask. So let's wait for the caching. It is done, and then we have the answer response thought. The text mentioned MacLoad as one of the locations where refreshment will be available during the networking break sessions at Inventure. From the context provided, it seems that MacLoad is a specific area within the conference center where attendees can grab a drink and a snack during the event, and it is likely a designed space for networking and refreshment, which is absolutely correct. It has done a great job in answering and retrieving the questions and retrieving the passages. MacLoad floor appears to be, so the final answer is MacLoad appears to be a design area within the conference and blah, blah, blah. Okay, so the probable document, the most probable document that is retrieved is document 3 with probability of around 1. And the second one is document number 1. And if you go to the documents that we have, you see that the document number 3, or with index 3, is the only document within the first 4 documents that the name of this place is mentioned. So that's why we have this passage has got a high probability. And that's it about the code that they have, and it was super simple to run that on Google Colab, but I have to mention that it was not quite as straightforward to set up the environment variables, like the changing the version of Hugging Face to resolve the conflicts. Thank you everyone for making to this very end. If you enjoyed this video, please share with your friends, because sharing means caring, and please subscribe to the channel and smash the sub like button so that you can stay tuned on the state of the art models. Thank you and have a great day.